So in this problem, we would like to use the Green-Stokes formula in order to compute a certain vector line integral. The Green-Stokes formula allows us to translate this into a vector surface integral for the curl of the underlying vector field. So why don't we begin by finding the curl of the vector field? So this is what the vector field is: y squared x z, and the curl is by definition, at least formally, the cross product between the gradient operator and f, which means that we will use the following determinant. So partial with respect to x, partial with respect to y, partial with respect to z, and then here we have y squared x z. And when we multiply a differential operator by a function, we simply take the derivative with respect to the corresponding variable. So delete the first row, delete the first column, and take the derivative of z with respect to y and subtract from it the derivative of x with respect to z. Obviously, both of them are 0. Then delete the first row, delete the second column, take the derivative of z with respect to x and subtract from it the derivative of y squared with respect to z. Again, we find 0, and the extra negative sign is not giving us much more. And finally, delete the first row, delete the second column. I'm sorry, I meant the extra negative sign doesn't give us more. Delete now the first row, delete the last column, and take the derivative of x with respect to x, that's 1, minus the derivative of y squared with respect to y, that's minus 2y. And that's the curl. Okay, so this is the vector field whose vector surface integral we should take. And in order to take this vector surface integral, we should parameterize this surface patch. It's not too hard because this can be considered as the graph of the function 3 minus x minus y, which means that we could use the parameterization g of uv equals u comma v comma 3 minus u minus v. This is what is known as the graph parameterization. It's defined exactly on the domain over which this is a graph, meaning 0, 1, cross 0, 1. Now, we should take the normal vector of this parameterization, which is simply g sub u cross g sub v. What do we mean by g sub u cross g sub v? Or what do we mean by g sub u? We mean the vector resulting from g by taking the partial derivatives of all the components with respect to u. So that will be 1, 0, negative 1. And what is g sub v? Again, it's what results from g by taking the partial derivatives with respect to v of all the components. So that's 0, 1, negative 1. And this gives us following vector: 1, 0, negative 1, 0, 1, negative 1. For the first coordinate, delete first row, first column, and you will get 1. For the second coordinate, delete first row, first column, take the determinant, we find negative 1. We have an extra negative sign that gives us 1. And then we delete the first row, the last column, that gives us 1. At this point, it might be a good idea to recall what we're looking for here. So basically, we want to take the double integral over the domain of the parameterization of the curl of the vector field f, composed with the parameterization, and dotted with a normal vector. Now, what we have to be careful about is that the normal vector should have the orientation which is compatible with the orientation of the boundary, and that's the upward orientation. What we just found is the right normal vector because the last component is 1, which means that it points upward. Of course, we should also recall the Green-Stokes formula. which tells us that if you have a circulation integral of f along the boundary of S, then this will be equal to the vector surface integral of the curl of f on the surface. And of course, these two integrals, these two vector integrals should have orientations on their corresponding domains that are compatible. Compatible means that if you are on the surface and you sit in the orientation of the normal of the surface and look toward the way that the path is traversed, then the domain should be on your left hand. That's an empirical way of putting it. So let's see how much we have computed so far. So we have this. We need to find this now, which means that we need to take the curl of f and compose it with g of uv. What does that mean? We need to take the curl of f, and wherever you see an x, put u. Wherever you see y, put v. Wherever you see z, put 3 minus u minus v. Now the curl is given by 0, 0, 1 minus 2y, so this will be 0, 0, 1 minus 2v. So finally, we need to take the dot product. Oops, sorry about this. We need to take the dot product of 0, 0, 1 minus 2v with a normal vector, meaning 1, 1, 1. This gives us simply 1 minus 2v. And finally, we need to take the integral over the domain of the parameterization, which is 0, 1 cross 0, 1. Of what? Of 1 minus 2v du and then dv. This will end up being 0, as we will see. So it's integral from 0 to 1 of u minus 2uv from u equals 0 to u equals 1. And then we need to integrate with respect to v. This will give us the integral from 0 to 1 of 1 minus 2v dv. And the antiderivative here will be v minus v squared from 0 to 1, which simply gives us 0. And that's it. It's a long computation. One has to take several steps. So you need to remember, of course, the formula itself, and you need to remember how to interpret the vector surface integral. So these two things in green form the basis of this exercise. And that's all. Thanks for watching.